So this part, this section also includes a concept that we haven't really seen before, but it uses again the same idea of derivative. You know that the change of y respect to x is given by the derivative of the function. You know, when we talk about instantaneous change. So now, rather than this be you know, talking about just the derivative, we're going to be able to split it into two pieces and say the differential of y is the derivative of f of x times the differential of x. So because the idea is that I would multiply both sides of the equation by the differential of x, or just simply dx. So if I do that, these two will cancel out and I just have dy. And so what would be the difference between dy and, say, just simply changing y or delta y? So if we see it in this picture graphically, the change in y occurs when I have an original x, and then I move away from this x some distance, some small distance that I'm going to call x plus, you know, change in x or a small change in x. So the difference in here would be of the two y's that I'm going to create by it. So in this case, this y comes from this x, and in this case, this y value will be originated from moving or from taking an x value that is a little bit different from the original one. Let's say x plus delta x. So the change in y is simply, you know, the change in y. Like I have 2 points, so I find the difference of the y's, and that's delta y. And compare it to dy, the dy from the derivative, from the differential, it always talks about that tangent line that we have. So for that small change in x, I'm going to have a quantity in here, a y quantity, that if this is the original y and this is the final y that I'm going to have after I change in x, but on my tangent line, and this quantity is the one that would be dy, not the one on the function, but the one that is referred to the tangent line. So and the way of finding it is the derivative at x times the small the dx that we may be given. And in here, in change of y, the only thing I have to do is find out how much is f of x plus that change in x, and subtract it from that f of x, and that will be my change in y. Now, because we're talking about the tangent line around certain point, you know that delta y and dy are going to be very close to each other. So it says compare the values of delta y and dy of this function, and x changes from 2 to 2.05. So you know that you were adding 0.05 to this. That's all you're doing. So for the change in y, the only thing that you have to do is find out how much is f of 2.05, and then subtract it from f of 2, and that will be the change in y. That's very simple. Now the dy, by formula, you know that is the derivative of f, and now we're talking about around the point 2, so you would do f prime of 2 times dx. Now this, if I do 2.05 minus 2, that will be the change in x, but the change in x happens to be the same as dx, so I know that dx is 0.05. So 0.05. So those are the two things that I have to do for dy. So as you can see here, that's already done for you, and the change in y, or delta y, is this, and the dy is this would be the f prime of 2, and this would be the dx that was given on the problem. Oops. You can see it. Well, you have your papers, so you can see that. This will be f prime of 2, and then this will be dx. And now, as you can see, dy is 0.7, and delta y, which is accurate, this is an approximation, this is accurate, it's 0.71. And you can do that for other values. So one of the applications for differentials, it says the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05. And this is something that it happens every day, not only because of humans mistakenly measuring, but also limitations on the tools that are used to measure. So it says, what's the maximum error in using this value of the radius to compute the volume of the sphere? So because you're gonna use this measurement to find another measurement, then therefore there's always so much that you can be off by. Otherwise you're really gonna be miscalculating, in this case, the volume. So the same idea with derivatives. If I have the volume equals 4 pi radius cube over 3, when I take the derivative respect to radius, this is different from related rates when we took the derivative with respect to time. When I do that, I'm going to have 4/3 pi radius. Well, the derivative of r to the third power would be 3r squared. These 3's will cancel out, so I have 4 pi radius squared. Now, if I multiply both sides of the equation by dr, this is what you have right here. dv equals 4 pi radius squared dr. So in here, what you know is the change in radius is 0.05. So if you consider the radius and the volume to be as x and y, like my independent and dependent variable, then I can call this my dr. So since this is my dr is given, the radius, which is 21 centimeters, is given. So I can find what is the error measurement for the volume, which will be in here 277. Since it's the error in volume, it is understood that it's centimeters cubed, because in here this will be centimeters squared, and then dr is given centimeters as well, and you have centimeters cubed. But what does this mean? 277 seems to be a very large number, but the other application of differential is that you can divide it by the original volume and then make comparisons relative to the original measurement. So for example, let me show you right here. It says if you were to find this is the amount of error for 21 centimeters, and that's about this much, or 0.24%, then the relative error that the volume will produce, well, you will have to do 277 divided by the original volume. So you find the original volume by doing you would do okay, I know that. You will do 4 times pi times 21 to the third power, and that divided by 3, and that will be the original volume. So being off by 277 probably is not that bad. 277 divided by, I don't know what it's doing. 277 divided by, okay, by that will be 0.007, and that's the number that you have then. So this is the error divided by the original volume. That's how much percentage you're gonna be off. So it is really not a big deal. Anything within 1% is probably fine. Well, everything depends. This has to be related also with tolerance. So if you're talking about the tolerance of the pieces that makes up an iPod or one of those smartphones, probably being 1% off will be a huge deal, and they will return those pieces to China for them to be remade again.